I left IBM because I'd been there for 39 years and I thought it would be okay if I left, right, honestly, right? It wasn't a lifetime thing, necessarily. But the idea of working with people in this quantum area with such a versatile technology was what really appealed to me, of doing these different things. And this thing here, people, sometimes you call them glass cells, vapor cells. We've recently started trying out calling them atomic prisms, which I think is pretty cool, especially with the light aspect of, right? Because who knows what a glass cell is, right? But an atomic prism is maybe slightly more descriptive here. How do you make these things? How do you design them? After all, it's not really easy to take a bunch of atoms and cool them down to close to absolute zero and design your latest inertial sensor. Albert is the code name for what we have as a quantum sensor design platform. It's been up on the cloud before in prototype form. It will come back up later this year. And the idea with this is, just like you can use quantum computers and other computers in the cloud, you'll be able to do this type of design on the cloud as well. So this is going to open up to physics students, to engineering students, to engineers and companies, the ability to now design this sort of technology much easier. And at the guts of it is exactly the same technology that we use for things like RF sensors, right? And other sensors and clocks like this. So you'll be hearing more about this. We're working on the name, you know, Albert Einstein. We're not so happy with that. But it's, again, an example of the reuse of what we're trying to do. Now, moving a bit over into quantum computing here. I'm showing this because it is Gorpy, and I know this is business, okay? But what I'm pointing out really here is what I mentioned before, is that somehow you have hardware. Think of your phone, right? Think of your laptop. Somewhere you have hardware. And then you've got software. And you've got some software that is very, very close to the hardware that controls that hardware. In the case of a lot of what we do is it can control the lasers. I mean, very, very simply, right? To do what? When are they firing? At what frequencies? Where? Right? And so forth and things like this. And you slowly work up this way. So one of our realizations here as a company, really this was a hardware company for a long, long time, was that we had to get into the software business. So we bought a company called Sutor. It's out of the University of Chicago, which is why we have an office there. And they are one of the preeminent software groups that do quantum computing software, both at the low level, but also at the higher application level. So I show you this because, you know, we could go into what we do with quantum, but now I want you to start imagining all the other types of quantum devices that may not have stacks that are quite as deep, but will have to evolve. So for any of you who may be in school, for example, you may be thinking of yourself as a hardware person, but ultimately you may end up as a software person. It has happened before. People have changed sides, okay? But the idea is that that's, as we know from the business perspective also, there's more money as you move higher in the stack. There's more margin as you move higher in the stack, right? So, okay. So once again, this is the cell. This is the same type. It's just not pink. Within this, at our Madison office, we have produced what I called the checkerboard before, an array of 35 by 35 atoms. So that's 1,225. I had to calculate that one too. Atoms. Fits within the width of a human hair. So as we talk about qubits, or anything else we want to talk about here, a qubit is the basic information unit in quantum computers. It means that in a very, very tiny space, and we believe we can scale these. Think of these as proto-qubits right now. We're not saying we can control them all right this minute, by any means, right? We think we can scale this up to around 10,000 eventually within one tiny cell. That's a tremendous amount of processing power and much, much smaller than anything you see. As an example, IBM has a They just installed at the Cleveland Clinic a 127 qubit machine with all of its refrigeration and electronics, and it fits into a 9-foot by 9-foot by 9-foot box. A lot of refrigeration. We can fit that in here, ultimately, right? And we can make it pervasive if, we get the photonics. So that's what we're aiming at, and that's what I'm trying to kind of impress with you, the targets, what we're going to try to do with the photonics and other technology that's going to be involved with this. Now, in terms of the ways of making, let's just talk about this general technology. I mentioned this word qubits. So a qubit is, I just said, it's the basic unit of quantum information. Traditionally, we use bits, zeros and ones. They've been great. They'll continue to be great. But nature isn't zeros and ones. Nature isn't digital, right? Nature is analog. And the way nature works at the very smallest level, right, is through quantum capabilities and things like this. And when we actually want to use these qubits, and you can use them as the atoms that are in a sensor or whatever, you have choices. And so you have companies like IBM, Amazon, Google doing superconducting down at the bottom. You have some pure photonic. You have ion trap, like Honeywell or Continuum, as well as ion Q. There are about 5 atomic companies like us. Not all of them work for everything. Superconducting needs a lot of refrigeration, as I've mentioned. There are other characteristics that does mean that you can probably end up making very large systems, but it's probably not what you're going to be using for quantum memory, and none of the sensors, right? Photonic is very, very interesting. So this is really pure lasers and mirrors and prisms and things like this, but it's very tricky, because as you know more than I know, photons tend to run away. And if that photon is a carrier of great information for you, it can be a problem if you lose it. Same happens with ions. Ions may not scale. The people who do ions think they're going to scale. But the problem with ions is ions are charged. I mean, that's by nature. That's what makes them an ions, which means that they repel each other, right? They want to push away from each other, which means you have to corral them and push them along, right, in different ways. And so it's not really clear in the long run how well we're going to be able to scale putting how many ions, as opposed to what I showed you with the atomic or neutral atom approach. We think we can get it up to about 10,000. First generation will be about 100, then about 1,000, then about 10,000. We'll have decisions to make at each point. So we believe that this is the most widely used technology rather, but really for you, right, coming from the photonics industry, you're cool with any of the first 3. Those are all photonic technologies, right? And so there are going to be other markets to sell into, such as quantum memory. I mean, we use memory all the time, right? I mean, this is a lot of memory. This is 32 gigabytes of memory. Quantum computer today has no memory, 0 memory. Eventually, we're going to need memory for that as well. Okay, so let's talk about quantum computers. Right? And this will bring us home on this. Classical computers have served us well. We more or less date the classical computer era from about 1945. There was a lot of work done during World War II that was then declassified in the middle 50s. We started shifting from what were great big calculators with punch cards to actual programmable computers. 1960s brought the mainframes. Then you started seeing the mini computers in the 1980s. You started seeing the PCs. Later in that decade, you started seeing laptops. 2007, you saw the iPhone, though there were some smartphones before that. So all of those are technologies, and it's all classical computing. It goes back to what we call a von Neumann architecture. And it's not going away, right? You don't need a quantum keyboard or a quantum display program and things like this. This is going to remain part of what we're going to do. But there are problems that are intractable. Now, intractable does not mean impossible, right? Intractable means somehow we could do this with more of something. So, you know, more money, so I'll do that from the business perspective. With more money, we could solve this problem. That's often true. More time, more memory, more energy, right? More of something. So there are problems in classical computing that say, yeah, we can do that, it just takes 2 million years. And arguably, we based most of our cybersecurity around such things, that you cannot break encryption in less than 1 million years, whatever the number is, right, depending on what type of encryption. And so we're really thrilled, yes, you know, you can't do it. Then a threat shows up, right? So on the good side, you want to make intractable problems tractable, except if they have to do with security, right? Unless you're a three-letter agency, and things like this. So example of these things are simulations of physical systems, right? Chemistry, I mean, that's your best example. Doing chemistry on a classical computer is very hard, very slow, and very inaccurate. And once you get above very small molecules, it's just hopeless, just absolutely hopeless, right? You know, we're really good at hydrogen at this point. We know a lot about hydrogen. We don't need to know any more about hydrogen, actually, as far as this goes. But, you know, development to new batteries, brand new materials, and ultimately medicines. Now, medicines, for all you may see about, hey, we're doing, you know, quantum for pharmaceuticals, it's a little bit like, well, get back to me in 2040, because we should have quantum computers big enough to do pharmaceuticals in 15 to 20 years, right? There's a lot of hype in this area. More energy efficient processes, such as catalysts, such as for creating fertilizers. Tremendous amount of energy, but it's approximately 3% of all the energy used in the world every year is used to make fertilizers. That's a lot. Take 1% off that, right? You're saving a tremendous amount of energy. Logistical optimization, we cannot solve the traveling salesman problem, but we can make problems that are completely intractable, large problems, we can bring them in and make them. We can't solve the largest ones, but we can solve larger problems in some of these types of cases. Combinatorial optimization, many-factor risk assessment, fintech. Fintech is a huge area. Financial optimization. And that's the golden, that one word, or three, financial services industry. It's the old joke, why do people rob banks? It's because they've got all the money. So you want a product you can sell to the financial services industry because they will sink thousands and millions of dollars into something if it has hope. And luckily, that's one of the three areas. And then we get into some other things like machine learning, computational fluid dynamics, which oddly enough is related to some of the math we use for machine learning. And then some of these other things. And one I mentioned at the end, breaking encryption protocols.